Hello everyone, my name is Kishan Chandan and I'm a PhD student at SUNY Binghamton. Today, I will be presenting our work on learning to guide human attention on mobile telepresence robots with 360-degree vision. And this work was done at SUNY Binghamton with Xiaohan Zhang, Jack Albertson, Xiaoyang Zhang, Yao Liu, and my advisor Shiqi Zhang. So let's start with what is telepresence. Telepresence is an illusion of spatial presence at a place other than the true location. In particular, mobile telepresence robots help the human operator to perceive along with the ability to move and actuate in the remote environment. Telepresence robots are used in several application domains like offices, search and rescue, education, etc. On the left, we see a telepresence robot from Double Robotics in an office environment, while on the right hand, we see an image of a rescue robot controlled remotely during the RoboCup Rescue 2018 competition. Recently, researchers have equipped mobile telepresence robot with a 360-degree camera to perceive the entire sphere of the remote environment. The 360-degree frames are often represented using equirectangular images, which can be seen in the slide here. To visualize the 360-degree videos, one can use a mobile device or a screen or a head-mounted display. The problem with using the mobile devices is that it makes it difficult for the human operator to perceive the frame because of the size of device. Mobile devices are usually not designed to visualize such content. On the other hand, one of the widely used methods of visualizing the 360-degree videos is using head-mounted displays. The head-mounted displays provide an immersive experience to the user, but the problem is that the human operator can visualize only a part of the remote environment. Now let's see why the human can only observe the part of the environment. Humans typically have a peripheral vision of about 120 degrees. Outside the peripheral vision, the human eye cannot visualize anything. HMDs are designed to mimic human vision system. HMDs also typically have a field of view between 90 to 120 degrees. Hence, out of the 360 degrees, about 240 degrees is out of the field of view. This results in human missing the information available outside the field of view. The gap between the 360-degree video capturing and the difficulty of human to process the all-degree view motivates our research. To address this, we propose a framework that for the first time equips mobile telepresence robots with the simultaneous capabilities of 360-degree scene analysis and guiding the human attention to the areas of interest. We call our framework as GAL 360, which is short for Guiding Human Attention with Learning in 360 Vision. Our framework tries to bridge the human MTR observability gap as well as it provides scene analysis using the 360-degree videos. We use a learning-based guiding for the human attention. Also, we use a particle filter that estimates the human motion intention in the remote environment. Now let's dive deep into the framework. The input to the frame includes a live 360-degree video frame of the remote environment obtained from the robot. These frames encode the 360-degree information using the equirectangular projection, and we refer to them as equirectangular frames. These frames are processed using an object detection system to output an analyzed frame. Now we will see how this object detection system is used in our framework. We use YOLO V3, a CNN-based object detection library for scene analysis. We divide the 360-degree video into 8 wedges, each having 45 degrees of information. Every wedge can be in one of the 4 shades, one where there are no objects in the current wedge. The other one is where there is a clutter in the current wedge, which means clutter here represents a lot of objects detected in the wedge. The third is the state where the wedge contains the object of interest. The fourth is the wedge which contains the object of interest but with the clutter. All of the states are represented in an egocentric manner to show the locations of the object with respect to the currently focused wedge by the human operator. The detected objects are then filtered to highlight only the objects of interest. Depending on the robot's current task, the object of interest can be different. We construct a sphere and use these equirectangular frames as the texture of the sphere. A user may only be viewing a part of the sphere at a time because of the limited field of view. The portion viewed by the user is called the viewport. At runtime, based on the head pose of the human operator, views in the viewport are rendered accordingly. The framework also contains a reinforcement learning based guidance strategy, which we call as a policy, which takes the input as the analyzed frame data as well as the current focus phase of the human and outputs an action to be taken by the agent. Now we will see how GAL 360 learns a policy for guiding human attention. We use reinforcement learning, specifically Q learning, to learn a policy for guiding human attention. The state space represents the state of every wedge. And since we have 8 wedges and each wedge can have 4 different values, we have 4 to 8 different states. The action space consists of 3 actions, which is the left action, right action, and the confirm action, where the left and the right actions are indicators, whereas the confirm action checks if the object is in the current wedge or not. Once the policy is generated, based on the current state of the system, the policy suggests an action, which can be a guidance indicator to enable the human to find the object of interest in the remote environment. Once the agent performs the action, it observes the reward R and the next state S dash. Finally, the tuple S, A, R, and S dash are used to update the Q values for that state action pair. We have used Burlap library for the implementation of our domain as well as the RL agent. Finally, the framework overlays visual indicators suggested by the policy in real time to guide the human attention toward the object of interest while providing an immersive 360-degree view of the remote environment. Now we will see how we implemented the human motion intent estimation in our GAL 360 framework. We used a particle filter-based state estimator to identify the human operator's motion intention. Each particle in the particle filter represents a state, which in our case is one of the 8 wedges. We initialize the particle filter with m particles, and the weight of each particle is 1 by m. The following equation shows the belief state of the particle filter. At every step, the evidence to the particle filter is the current change in the human head orientation, whether it's left or right, and the current focused wedge. Here is the equation we used for belief updation. The threshold density of the particle was set to 70%. The particle filter outputs the predicted human intention once the density is above this threshold. Finally, we use a controller that sends a control signal to the robot based on the predicted human motion intention that moves the robot in the remote environment. Now we will see the telepresence interface that we developed using the GAL 360 framework. The interface shows a 2D map with the live location of the robot. It also shows a window with a 360-degree video where the human can use an arrow to move around. To indicate the teleop input, we highlight the arrow keys. A 2D icon shows the human head pose in the 360-degree view. The interface allows the human to adjust the size of the window as well as the field of view using the slider. Finally, using the VR button, the 360-degree video can be viewed in a head-mounted display in the VR mode. We have tested our framework in a target search scenario where there were different target objects in different environments. We used a Segway-based mobile platform called RMP110 for collecting a dataset of the real world. We used a 360-degree camera, Ricoh Theta 5, to capture the 360-degree videos. We used 2 Matterport 3D environments, one which was a home and one was the office environment. And also we created one real-world office environment as the dataset. The figures A and B show the home environment, whereas the figures C and D show the office environment from the Matterport 3D dataset. The figures E and F show the frames from the office environment dataset that we collected using a real robot. Now we will talk about the baselines that we use to compare with GAL 360. The first one is the monocular fixed orientation that has about 120 degrees of field of view. The second is an all-degree view, which has the 360-degree field of view of the remote environment. The third is the fixed guidance strategy that we designed. And the fourth one is the RLGS, which is the reinforcement learning based guidance strategy which is an ablation of GAL 360 without the particle filter for the human motion intention estimation. We compared the cumulative reward that the agent received using the baseline FGS as well as the GAL 360. We tested 150 different policies after each batch of 100 episodes in our realistic simulation. The x-axis on the figure represents the number of episodes, and the y-axis represents the cumulative reward. From the figure, we can observe that the learned policy performs better than FGS once it's mature enough. Now we will provide a demonstration of our GAL 360 framework. Using the interface, the human starts to look around to find the target object in the remote environment. Under the hood, GAL 360 constantly uses head motions to drive the mobile robot platform in the remote environment. Once the human starts looking around, visual indicators are used to guide the human attention. The human stochastically follows the visual indicators to find the target object. We terminate the trial when the robot reaches the location of the target object and the human can find the target object. Now we see the policy after 3000 training episode, which is the early learning phase of the policy. The policy is frequently misleading in guiding the human attention. The human is not able to find the target object in the remote environment because the policy is distracting the human. The policy shows the indicators and the human stochastically tries to follow the indicators. For a long time, the human gets distracted and cannot find the target object. Finally, the human is able to find the target object and the trial is terminated. Now we'll see the result after 15,000 episodes of training. The policy now is able to suggest indicators that can efficiently and accurately guide the human attention to the target object. We also created a virtual environment using a dataset collected from a real robot, RMP110. You can see that the robot is being teleoperated in an office environment to collect the dataset. On the top, you can see the FPV 360-degree video being captured. Now we'll see the late learning phase results in the real world. GAL 360 is again able to efficiently and accurately guide the human attention towards the target object in the environment that we created using the real world dataset. And the human is able to find the target object in the remote environment. Now we'll see the results that we obtain after comparing GAL 360 with the 4 different baselines that we talked about. The first figure that you see is from the Matterport 3D dataset, and we use a home environment from that. The x-axis on that figure shows the distance of the robot from the target object, whereas the y-axis shows the average time in seconds it took for the robot to reach the object of interest. Comparison was done between the task completion time at 6 different distances. We see that GAL 360 took the least amount of time compared to the baseline to find the target object. 2 more environments were used. One of them was the Office Matterport 3D environment, and the other one was the real robot office environment dataset that we collected. We observed the same trend of results in all of those 3 environments. Finally, I will summarize the contribution of our GAL 360 framework. We designed a novel framework called GAL 360 for the mobile telepresence robots that enable 360-degree scene analysis while simultaneously guiding the human attention. Moreover, we designed a learning-based guidance strategy. Also, a particle filter-based human motion intent estimation was used to move the mobile robot platform. We evaluated GAL 360 using target search tasks in the photorealistic simulation that we developed. We used 2 environments from an open source dataset called Matterport 3D, and 1 environment was constructed using the real robot. We observed significant improvements in the efficiency of the human robot team in comparison to the competitive baselines. Thank you for listening.